All right. Oh. So, a couple of things before we get going. I put up your problem. Here I say week 9. I'll probably change this to be week 9 and 10. This nonlinear relationship stuff is probably going to take us not just this week, but probably next week as well. So I've got a bunch of different data files that we'll be using and looking at. I've got the do file that I'll kind of show you today, and then we'll kind of be working with, and then the slides for the week as well. So this will probably be not just week 9, but I can go ahead and change it either right now. This will probably be a lot of what we do for next week as well. Okay, so weeks 9 and 10. So what a lot of you are probably interested in is not what we're going to cover the next 2 weeks, right? What did you get in the exam? So I realized that time was kind of a constraint on the exam, so I kind of wrote it as on purpose to be that, because it's not only can you regurgitate or answer questions, but like how quickly. So I'm almost through grading them. I think I only have the last question, short answer question left, and I should have those done some point tomorrow. I don't know if I'll post them during the day tomorrow. I might hold off and kind of post them right when we kind of start, or right before we start class on Thursday. I'll have those exams with me to kind of hand back on Thursday. So I'll try to get over here as quick as possible from my other class. Can I get those handed out to those of you who are here? I don't have, so I'll tell you a little bit of inside baseball. So what I do is I don't look at names when I grade these. So I just kind of go through and I kind of grade every single problem. So I want to do it in order. So I'll grade all of problem 1, all of problem 2, kind of go through the exams that way. So I'm kind of grading consistently through every problem. I don't know how any one of you did, so don't ask me after class because I have no idea. I haven't looked at names and scores yet. Tomorrow, that's where I finished grading that last question. I'll start to then enter scores kind of from each problem to kind of see what your total grade was. I can guess, so just looking at the multiple choice, that average was about what I would expect. So it was right around getting 7 out of the 10 correct. I'd like it to be a little bit higher, but I understand, I wrote some of them a little bit more difficult, and I also give partial credit for the short answer. So I often expect the average to be a little bit lower there in the multiple choice, because I try my best to give points on short answer questions for, I'm not the hardest grader. I get that there was a lot of information. It's 6 different questions to kind of work through. But I'll tell you right now, the variance on the scores, I imagine from what I've graded this far, which is 90% of the exam, very fat tails, right? So what does that mean? When we talked about distributions, I'm thinking about test scores here. What does fat tails mean? It means that a lot of people did really good. A lot of people did really bad. I have some collected information in terms of how many of these in-class quizzes were you here for. I have whether or not you were here the day before the exam, which I stress the importance of. I likely will have some results that we take it just a gander at on Thursday about the correlations and run some regressions with those, as well as some other controls. My imagination is there's a high positive correlation. Probably speaking to the wrong people. I see a lot of you a lot of the time. Higher likelihood you're in this tail, right? If you've been kind of actively participating in class and showing up. I mean, there's questions where I literally gave you guys a p-value and I asked you to make a rejection decision. And some people didn't use that p-value to make the rejection decision. I mean, guys, how many times, what you reject when the p-value is less than what? Alpha. I mean, this is something we use almost every single class for the last month plus, right? So there was a couple questions where I could tell if someone probably was attending class or not. Once again, didn't look at the names. I don't have any idea about that yet. But some of these questions where I was trying to give easy points, people got them wrong. So I imagine there will be some pretty low test scores, right? If you're active in this class, you're showing up to class, I think there was a lot. Again, it was probably a difficult exam, right? Arguably, there's a lot of questions. You had a lot of not as much time, so I get that it was tough. But some of the kind of easier points in the exam, I still saw people missing. That probably tells me that you're either not showing up to class or you're not actively participating, or at least paying attention, right? Because when I'm asking you to make a rejection decision based off a p-value, that should have been a point every single person got, okay? So I'll have these Thursday. I'll kind of hand them back. I get this class is tough. Like that's not lost on me. I'm sure if there's like I don't know what they all are. There's probably apps and things where people rate different courses and things like that. Within the econ degree, my imagination, this is going to be in the top 3 most difficult. I could be wrong. I don't know. I haven't looked it out there. But this is a tough course, right? It's a lot of statistics, which isn't consistent with the vast majority of an econ major. So it's kind of a little bit different in that respect. And we do, some tough stuff. So I want to be kind of fair in grading. I expect a lot out of you, but I also, want to grade you fairly. What I will likely do, since you're here, all of you got maybe a little bit leg up on people who weren't, because I won't post the recording until after Thursday's class. You will likely tomorrow see an assignment pop up. I don't know how many points it's going to be worth yet, but it's probably a way that you can earn back some points or get points added to your exam score. Right? So it'll basically look like another short answer question that maybe I didn't use on the exam, but maybe had waiting just in case. I'm guessing it's going to be roughly 10 points would be my imagination at the most. You'll have basically until next Tuesday's class. It's a pretty short window, right? But you'll have some time to kind of work on that, submit that for Tuesday's class, and kind of have an additional opportunity to earn back some points. Now, everyone should do this. I don't know why anyone wouldn't. You're not required to, I guess. But if, I'm not saying they're free points, like I still will grade them, like to make sure you got the correct answers, but it's a way that you can earn back some of those points on the exam, hopefully kind of getting that average where I typically like to see it. Once again, I haven't totaled up everything. I don't know exactly where the average is, but just based off of what I've graded, I imagine, like I said, it's going to be somewhere around 10 points, maybe a little bit less, but we'll see. So look for that to pop up tomorrow. I'll mention it again in class on Thursday, but for those of you who are here, gives you a little bit of a kind of a jump start on that, kind of get working on that early. Okay. Once it's up there, I'll have office hours next Monday. I don't mind if you stop by and ask for some just clarifying questions or kind of working through things. I'll be here on Friday. I don't have like official office hours, but if you send me an email, I can likely make sure I'm in my office if there's a time that works for you to stop by. I try to provide all these tools for you guys to kind of, even the office hours I reserved right before the exam. I would have liked to see more people kind of stop by that day. I would have thought there would be more people, but maybe that's why I had a fat left tail as well, right? So that's kind of where we are in terms of the exam. I guess I'll have those on Thursday to hand back. Look for that additional kind of assignment to earn back some of those points. Other than that, questions from me before we kind of jump into our next kind of topics. Okay. So, I get that it was a lot of questions to kind of work through. Time was kind of an issue. But were the questions, give me some honest feedback. Were they wildly different than what you would expect? At least the types of questions I was asking? Getting some no, some, there's probably a few. There's a few I threw on there. Separate the A's from the B's, right? I would probably a little bit less focus on in class. But if you're looking at that practice exam, maybe think about the final. I would just take a look through that practice exam kind of set I gave you, look at the actual exam once you get it back, kind of see what some of the similarities there are. I tried to stress like focusing on really those questions that were on that practice exam. Also, some of the stuff that we worked through in class, I didn't do it, for no reason. I specifically remember working through some examples where we talked about what changes the F statistic and makes it more or less likely. And lo and behold, there were 2 questions in the same problem that asks you the exact same thing. So I'm trying to kind of give you stuff in class that's representative of what you'll see. I don't know, maybe you're all probably MFing me over the weekend and they're all pissed off at me. But I think by the time we kind of get everything ironed out, this additional assignment, I think scores will kind of be about where I'd like to see them. Okay. But this also brings me to the point, the exams are tough, right? So where's some easier problem or points you can get, these problem sets where you've got plenty of time to come ask me questions, make sure you're getting many points as possible on those. Those will kind of help kind of balance out maybe any kind of a little, bit of poor performance on an exam or some questions you can miss there, okay? All right, any other questions before we dive into new material here today? Nobody has any questions? Yeah.
I think I've already asked this, but just to confirm the final, it's what we do to do till the end of the semester.
Yep, but you'll even see today. So it's not cumulative, and I'm not going to go back and ask you the types. However, we'll even see today, we're gonna talk about doing tests between restricted and unrestricted models in a different context. But yeah, in terms of the types of questions from here on out, it'll be only stuff that you would see on practice problems from here on out, that practice exam. Yeah, it's not gonna be cumulative in the sense of like day one stuff.
Okay.
Yep. Excuse me. And I don't know if I'll get them up tomorrow. I might get a set of practice problems up. We're not gonna have a quiz yet this week. We've got to work through some more material before we get to that next quiz. But you might see some practice problems pop up there relatively, soon. Like I said, maybe tomorrow if I get enough time. If not, likely on Thursday. In between my classes, I'll probably get those practice problems solidified and up there. Okay. All right. So what we're going to talk about today is up to this point, we've only ever estimated what we would call linear relationships. So we're calling this simple or multiple linear regression, right? We can actually estimate things that are nonlinear. And I alluded to this, I think, in a class period or two, but we'll dive deeper into today. So our typical regression equation, right? Maybe even if I asked you to write out a regression equation on the exam, right, would have been you took that dependent variable and it was going to be some function of this independent variable, right? So you have an intercept and you have a slope. So it's just looking like y equals mx plus b. So we didn't maybe explicitly say this, but when I'm interpreting that slope coefficient beta 1, I can think of it as what? So if I have something like this, I've got my air turn. If I wanted my marginal effect, or what was the effect of one more unit of good x, or a change in x of 1 unit, well, what's that the definition of? Change 1 unit of x changes our predicted y value by whatever that slope is. Our marginal effect for a simple linear regression model, all we were really doing is taking a derivative of this function, so the change in y, from a change in x, right? All that would be was whatever that slope coefficient estimate we found was. Now, I think the example I have in the slides, and we'll kind of jump the gun here, but I think it helps to see me draw these things out maybe. Let's say I'm trying to, seems stupid, but let's say I'm trying to estimate the length of a fish based off of its age, right? So I've got this pond of fish. I don't know, these researchers start catching them, right? Measuring them, kind of, I don't know, however you carbon data alive, we're going to figure out how old it is, right? And we had all these different ages for these fish and then their length. Well, if I try to estimate a linear relationship here, well, I could draw like a line that kind of best fits the data here, but it doesn't really fit the data over here, right? So that I could draw like a line that best fit here, but it doesn't fit the data here. And in fact, when we're estimating a linear relationship, I can't estimate these multiple lines. I just want one line. If I tried to draw something that best fit this data, notice like I'm pretty far off for all the values in the middle here. Right? It's really hard to come up with one line that really best fits this data because it had some curvature to it. Right? So if I wasn't forced to make this linear, what would be something where I could minimize those errors I'm making? Have something that had some curvature to it, right? So that's what we're essentially going to be diving into today. And we sometimes know that the relationship isn't going to be linear. In fact, it's going to be nonlinear. And how do we do that? You think about a fish, think about this in terms of humans, right? As you get 1 year older, what initially happens to your height? You go from 0 to 1, you shrink. As you get 1 year older, what happens to your height? But what happens? Eventually, all of you right now, what's happening to your height as you get a year older? Maybe some of you are lucky and you're still growing a little bit, right? But it's pretty much tapered off, right? You have this increase in height based off your age, but eventually it kind of tapers off as you get older, right? Same idea with fish, right? So initially, those first couple of years of a fish's life, they're growing dramatically. And then they get to be 5 or 6, they basically are the same height, right? So we know that there's going to be this nonlinear relationship. How can we estimate this? Well, this simple linear regression, we said the effect of being 1 year older was whatever that slope coefficient we found was. If instead I had this regression where I had not only age, but I had the age squared, right? Well, now I've got what, y is equal to a plus bx plus cx squared. I've got kind of this quadratic relationship, right, between this x variable and my y variable. I put age in both places. This is why I need to write before I talk. We're predicting the fish's length, right, based off of its age. So we have this kind of quadratic relationship. We're not making it linear anymore. We're allowing it to be nonlinear. So if I now think about, and I'm jumping the gun a little bit, but we'll talk about it more in depth in later slides. Here we said this was kind of like the marginal effect of being 1 year older on the fish's length if it was a linear relationship. What's the marginal effect of being 1 year older now? Well, I'm taking a derivative of this function in respect to that x variable, right? Whatever I have on the right-hand side. So it becomes not only my slope coefficient on the nonlinear component, but then 2 times that coefficient I see on the squared component times the actual value for h. So with a nonlinear relationship, the effect of being 1 year older, notice it will depend on what age the fish is. Or if I was estimating it for humans, the effect of being 1 year older is going to be very different if I was going from age 5 to 6 compared to 55 to 56. Right? So my marginal effect when I have these nonlinear relationships will not be a constant value. Right? It's actually going to be a function of whatever that x variable is. Okay? So my marginal effect will be changing depending on the age of the fish, or in my other example, the age of the human. Okay? So this is essentially what we're going to be doing. We're going to be including these squared terms and then say, okay, can I say that this relationship is linear? Is it nonlinear? How do I use some of my stata output, my kind of regression analysis output to actually make these statements? Okay? Any questions over? Yeah.
Since we're using the same variable, it was the second slope coefficient is equal to the square root of b1.
This slope coefficient?
Yeah.
The square root of, not necessarily, right? So if you're thinking about, yeah, so we'll go through some examples later, right? Beta 1 could be positive, beta 2 could be negative. And then you could have both of them be positive, right? And just because this is linear, you could have different, this could vary quite a bit, so it doesn't necessarily have to be, this coefficient isn't necessarily a function of this coefficient. Is that what you're asking me?
Yeah.
Yeah, doesn't necessarily have, now, you could think of how is the marginal effect changing with age, and then it would be some ratio of the coefficients, but this coefficient doesn't have to be a function of the other one. Is that, that's what you asked, right? Yeah. Any other questions before we keep moving here? All right, so. You know, we would think that as a fish gets older, the length goes up, right? But we said, just because we have this linear relationship, and here's where we got to be careful. I can estimate a linear relationship, and especially with a relatively high sample size, higher sample sizes are always going to make it what? Easier to reject, right? So it doesn't matter what type of test we're doing. We said higher sample sizes, easier to reject. That could have been testing joint significance, individual coefficient significance, because having a higher sample size did what to our standard errors? Decrease them. Right? Another kind of common mistake I saw in the exam. I have different sample sizes. What happens to my expected coefficient value? So if I have different sample sizes, the expected sign of the coefficient doesn't change at all. This was the idea that they're all still centered around whatever that true effect are. It's just changing that variation in the estimates I'll see, or it's only changing my standard errors. Okay. So here I've got a regression where age is explaining 70%, right? Look at my R squared. 70% of the variation in length is explained by the fish's age. Not crazy, right? You know, and the age variable, I could say, highly statistically significant, has a p-value of 0. The test statistic is 41, right? This is high statistical significance. But just because I estimate this as a linear relationship, it might be that the relationship between age and length is so strong that it looks like I've got a good regression here. Pretty high R squared, high statistical significance, but it could be that the relationship between age and length isn't actually linear. It could be that I could get an even higher R squared if I allow there to be some curvature, right? If I allow this to be nonlinear. So, I kind of tried to draw this ahead of time, but like, you can almost imagine if I had something that looks like it has like a little bit of curvature to it, there's like lines of best fit that better fit the data for different values of X, right? Or you can think about if I had this nice line that had some curvature to it, maybe I can actually minimize my errors with this line that's not linear. Okay? So how can I do that? Skip ahead here, because I kind of already alluded to this. We can just include a squared term. So if I'm doing this in Stata, right, how could I run this regression fairly quickly? Well, I could create a new variable that was equal to what? Age squared, or the way that we would actually do this in Stata, age times age, right? We'll end up seeing with the code eventually here. I'll show you some. You would multiply the variable by itself. Now that I have this new variable, which represents age squared, I just run this regression that includes not only age, but this new variable I created, which was age squared. Okay? So I think before we get too deep into this, just to kind of get used to going back to Stata, we went a little bit away from that kind of talk and getting ready for the exam. I've got this, and I don't think it actually, I've got to reset my global path. Oh, no, I was gonna say, I don't think my global path is working here. So we're gonna go to File, Import. One of the files is a CSV file that's sitting there on Canvas. This crashed in my last section, Stata, so we'll see if it does it here. I don't know why, it's not that large. But I had this kind of SMB data, and I think the slides say bluegill. I think when we open this up, I think it's actually smallmouth bass. So I changed the type of fish. Who knows why I did that, but I did. Yeah, I think it's smallmouth bass here. So we'll go to okay, importing that CSV file. I've now got all these different fish, their age, their length. It's like I'm missing the weight variable. That's just something I kind of grabbed off the internet. Just thought it'd be kind of an easy, quick data set we could look at. So I've got that opened up. I'm going to rename final age just to make it make a little more sense. I'm then going to run this regression. I could look at the scatter plot. We've already done all of this. So this was where we got that 44 as our coefficient on just looking at a linear relationship. Scatter plot will take a second. Here's what the data looked like. Looks like probably could better estimate this with something that's not quite linear. So this is one good way of, like, if you're thinking about there might exist a nonlinear relationship, just look at the scatter plot. Right? It generally will kind of give you an idea about, and this one's close, right? So we then need to come up with some ways that we say, okay, it looks like it could be linear, maybe not. How do I use statistics to tell me whether or not the better relationship, or the relationship, if I estimate this regression, will produce smaller errors, right? Minimize the sum of my squared error terms. How can I identify if that should be linear or nonlinear? So the way that we'll do that is I'm going to create this variable, which was age SQ, right? Just taking age, multiplying it by age. Okay. In fact, let's see. I don't think you can do this, but you might be able to. See if I do age squared. Oh yeah, so you can do age squared as well. I always just kind of set it up this way, just to make I don't know, thinking about what I'm doing is actually taking that age variable, multiplying by age, but you can do it either way. I'm then going to run that regression where I include length, age, and this new age squared variable. I mean, you can kind of see, right? 3 becomes 9, 2 becomes 4, so on and so forth. So I'm now going to run this regression where I've got age and age squared as my independent variables. And we'll kind of compare the two. So originally we had an R squared of 0.7, right? When I include the squared term, what's happened to my R squared? Well, this is kind of working just like it did before. I've really added in another variable. So what should happen to my R squared? Should go up, right? So anytime I estimate these nonlinear relationships, I mean, nothing is, I guess there are some things, but in practice, most things are not a 100% linear relationship. So by adding in this squared term, we're always going to be able to increase R squared a little bit, right? So we went from 0.7 to 0.75. So just from looking at the R squared, it looks like maybe this nonlinear relationship is more accurately capturing the relationship between age and the length of the fish. I can also look at evidence of that as, well, what's true about the statistical significance of the slope coefficient on my squared variable? It is highly statistically significant. So I have two indicators already that this squared term, right, estimating this as a nonlinear relationship, is more accurately capturing the relationship between this x and y variable. So looking at our r squared, looking at the statistical significance on the coefficient on the squared term, both two good indicators or statistical support for why that nonlinear relationship is better. Now, if I were to think about comparing this model where I included age squared to where I only had age, if I want to know did it increase the r squared to a statistically significant amount, what does that sound kind of similar to? So I have one model where I have an additional variable. I left it out here. Generally, we're doing this for multiple variables, but it's kind of like I can think about joint significance. Right now, I only have one variable here, so it's not really technically accurate to run these tests, but you can, and you'll get very similar results. So here, I'm only going to have one restriction, so it gets to be kind of weird. But what was that restriction? So I could use that test command. And I'm just going to test that age squared variable. So what it'll do, run both regressions, take the r squared from the unrestricted model, the one that treated this as a nonlinear relationship, r squared from the restricted, which was just linear. Q, my number of restrictions is 1 here. I don't have any additional controls, so my k would be what? 2, the number of variables in my unrestricted model. I can run that joint significant. Now it's not joint here, I only have 1, so it's not technically accurate, but I can still kind of see, oh, yeah, I was able to run these joint significance tests, and my second model that was nonlinear explains more of the variation that exists in that length variable. So these are all tools that we've already talked about, right? Yeah.
In order to reject, can you use both of those statistics, like the app, just like comparing it to like?
Yeah, so another common mistake I saw on the exam here, when we're looking at joint significance, we can't use the standard normal values as our approximate cutoffs. Why? Because that was standard normal values were the approximate cutoffs when we were looking at individual coefficient significance, and that was comparing a student t to a standard normal. We said as we get higher sample sizes, the student t becomes very, very close to the standard normal. What's true about joint significance? We said that comes from what distribution? The F distribution. Why was that a little bit different? We said for the F distribution, we were only ever looking at what tail? The right tail, because when we were calculating that F statistic, what was it actually telling us? Did we explain more variation from the unrestricted model? When we add in variables, we already said it earlier, what has to happen to the R squared? Goes up. So you always know the unrestricted R squared has to be greater than it. So you know this F statistic will always be positive. We were only ever looking at that right tail. So those standard normal values don't have any real meaning for us when we're looking at joint significance. So if I give you output like this, you can't really use that F statistic to compare it to 1.96 or whatever the level is you're looking at and using the standard normal. But you've got the p-value right here, right? This is the probability that you have that F statistic or anything greater. Is this statistically significant at any of our benchmark levels? Asked in kind of a weird way, but if it's 0, at all, right? It's less than every single alpha. So we have a highly statistically significant coefficient on that squared term, or sorry, we have a highly statistically significant coefficient on the squared term. And when we run the test for joint significance, although it's only for one restriction here, we find a similar thing, that we were able to explain a statistically significant amount more of the variation in y, or that we saw a statistically significant increase in our R squared. We'll always see an increase. This tells us if it was a statistically significant increase. Any other questions on this before we keep moving? And I've got some more complicated ones we'll look at here in just a second. So, oh, I want this slide. There we go. So when we estimate these nonlinear relationships, essentially what we're getting, and it kind of depends on the example. Because for like our length of the fish one, we only ever saw like this portion of the curve, right? We saw that it was increasing at a decreasing rate. We never saw ages to where it then started to decline, right? So it's all gonna be context specific and kind of the variables that we're looking at. But in general, if we have a positive coefficient on that square term, it's telling us that we have a convex relationship. And we'll walk through more of the four different kind of combinations we could have, increasing at an increasing rate, increasing at a decreasing rate, decreasing at a decreasing rate, decreasing at an increasing rate. But just to kind of capture what that sign tells us, the sign in this squared term, if it's positive, we've got this convex relationship. If it's negative, we've got this concave relationship. And I think this will make more sense as we start to work through more examples, but we care about the sign of that coefficient. Okay. So if we thought about the age one before we even ran the regression, well, we know that age is probably increasing length, right? But at a decreasing rate. So if I'm just thinking about the visual here, think about it's likely that it's increasing it at a decreasing rate. Now, that decreasing rate, what is that really? That's just the slope of my effect, or the slope of my kind of change in that y variable. So I would expect that if I run this regression, I see that age has a positive coefficient, but age squared has a negative coefficient. So we'll go ahead and kind of think about, do we actually see this? Sure enough, I run this regression with age and age squared, and I see that age is increasing length, but at a decreasing rate. And I'll show you something else that will kind of, I think, help with that. So we've got 79 and about -5. So if we go back to thinking about this marginal effect, what's the marginal effect of being 1 year older? Well, it's right here, right? If we find that beta 1 is positive, if I'm thinking about visually, if I have different ages and I wanted to plot out the marginal effect. When age is 0, what's the marginal effect here? 0 times anything is. So what's my marginal effect? Yeah, just that coefficient on the linear term. Now, as age goes up, if I found, so this, remember, was like 79, this was negative, I forget, -5 something. So what's happening to my marginal effect as the fish gets older? Being 1 year older starts to have a smaller and smaller effect, or my marginal effect is decreasing, right? Getting closer to 0. Okay. So we could kind of graph out our marginal effects, but where did this really come from? Well, when we're thinking about just looking at age and length, our line of best fit looks something like this. If I'm calculating marginal effects, hopefully it looks like this, but if I'm calculating marginal effects, what is that? It's the change in my y variable from a change in x. What is that for a line? Change in y over change in x is my slope, right? So what's happening? The slope is doing what? Decreasing, or the marginal effect is decreasing here, right? So all that marginal effect is telling us is if we were to look at that scatter plot and look at our line of best fit, what's happening to the slope for our line of best fit? Now, before it was just linear, right? So we just had one number, so it wasn't very interesting. Now we have that for different values of that x variable, our marginal effect is changing, right? In this example, it's decreasing. Yeah.
This is just the second derivative.
This?
Yeah.
Yeah, right. We're just looking at basically graphing out, not the second, right? We're just taking the derivative, right?
Right, but that's already a derivative. I mean, of the original function.
Yeah, so this was like y, this was where we were just predicting length based off of age.
Yeah.
So this function that we had for y, the change in it, right, that was just taking a derivative in that in respect to age.
Yeah.
Yep. And then just graphing out what that effect would be for different values of x. Yep. Any other questions before we keep moving here? Okay. So. What are maybe some other relationships you can think of? So this is one that I had, and we have got some data that kind of lines up with it. But we'll talk about this more first. So. Let's say you're thinking about, I already mentioned the one of like height and age, or for humans. What about exam performance? What if that was a function of how much you study? You don't study at all, 0 hours, and then you go from 0 to 1, right? 1 hour study. What do you think the effect of that first hour you study is? Well, you just went from not recognizing any of the terms used to like, even if you hadn't been in class the entire semester, at least you have some, right? You just went from probably getting a 0 to at least like, I have some idea of what's going on, right? So initially, as you study, there's going to be a large impact on your grade or on your performance, on your test performance. Now, by the time you get to like that 20th hour study, what's the effect of going from the 20th to the 21st hour? Not much. In fact, I'll draw an example. For me, I could argue by the time I get that high, it might start to become negative. I might start looking at things that aren't even going to be on the exam and I'm just confusing myself, right? So what's that relationship going to look like? Well, we're thinking about that it's increasing at a what? Same kind of type of relationship we had for the bluegill's age and length, right? Now, what can be the case, just to kind of make this point, and we'll dive into this a little bit deeper later on. But if I'm thinking about that marginal effect, right? So once again, if I'm thinking about here, I've got hours studied. I've got my test score, and then we want to map that out to marginal effects. Okay? So remember, the marginal effect of a 1 hour change in my X variable now would be, oh, I forgot the 2, times 2 times the actual value of X. Okay? Well, if I think that the relationship looks something like this, that as I study more, it's increasing my test score, but at a decreasing rate. Well, we said we then thought this was positive, this was negative. Now, you can imagine you could end up with a marginal effect that even though it starts out as positive, I guess I should put the predicted values in here, there could be a point where it actually starts to become negative, right? Or where this test score starts to decrease. Right? Now, in practice, a lot of the relationships we look at, we aren't looking at X values where we ever actually see it flip. We can, and we'll look at some of those scenarios probably more next class. Usually we're only looking at kind of like 1/2 of a convex or a concave relationship. But in theory, we could see the marginal effect actually go from being positive to being negative. So this is the kind of, hours studied performance on the test. Maybe you could argue at a high enough level of hours studied, maybe you actually see test performance start to decrease. So we can actually estimate this relationship. So I think I kind of left this out, but we've got a data set here. And once again, I'm pretty sure, where is it at? Test scores class. My path is set wrong, so I'm just going to go and open up the file. I think I have it set to be for my laptop and I forgot to change it. So we'll do test scores class. It's a much smaller data set, makes it a little bit more manageable. I don't want to save anything here. So I've got a bunch of data. I've got some ethnicity, I've got gender, grade. I have their performance on these standardized math and reading tests. I think this was North Carolina data that I had. And then I also have this, where is it at? This effort, which was their self-reported hours of study on average each week. So we're going to think about, can we estimate this student's math score based off of the effort that they're putting in, the average number of hours they study each week. So I could estimate the linear relationship. So I kind of have that right here. Right? I could then create this effort squared variable, right? Once again, I just kind of multiplied effort by itself to do that, and then run that regression. So what do we notice has happened? Well, my R squared has went from 0.01 to 0.02, so it's increased a bit. Anytime we include an additional independent variable, here it's just a square term, we always should see that R squared goes up. Now, if I'm looking at this squared term, here's where we kind of have to we want to be careful. At our conventional statistically significant levels, can I say that this added variable of effort squared actually has a statistically significant impact on predicting this math score?
No.
Not quite. That p-value is 0.11. It's not quite less than 0.1. Now, in practice, what levels could I reject at? If 10% significance corresponds to 90% confidence, here I could still reject that, like what? 88% confidence? Seems like I probably shouldn't just ignore this result altogether. It doesn't quite meet our standards, right? But it's pretty close. And I have a pretty small sample size, right? So statistical significance is going to be a little bit harder to come by, right? When I have small sample sizes. So here we're going to have this evidence that maybe there's a nonlinear relationship, but not at our conventionally statistically significant levels. Now I could run like a joint significance test here. Once again, it's not quite what we would do in practice because we're not really testing joint significance. We only have one variable. But what we could do is come down here and I'm going to create another variable. So I can estimate not only squared terms, right? This quadratic relationship, I can estimate cubic relationships, right? So I could now add in an additional term. I think in the slides here, just to skip ahead here a bit. I can include a cube term for effort as well. Right? Now, here I've got both my squared and my cube terms. So if I go back and run this regression, I'll have my new cube term, and I'll kind of run this here. Well, now it looks like both of these terms added in provides no additional amount. I mean, neither of these is even close to statistically significant, but I can test for joint significance of these two terms as well. How would we do that? We just use that test command. And what are the two restrictions I now have? These added nonlinear terms, both the squared and the cube term. So if I run this in Stata, I now have things that kind of line up. Notice here, if I were to just look at the individual significance of the squared or the cube term, neither of them are even close to being less than 0.1. In fact, even if I run the joint significance of including both of them at the same time, I'm getting a p-value of still 0.27, nowhere close to those kind of traditional benchmark values we were thinking about, 0.01, 0.05, and 0.1. So here I don't have any evidence that this cubic relationship. Now, if I do it this way, what am I actually comparing it to? If these are my two restrictions, here I'm comparing my cubic relationship to the. So it wouldn't be the squared one, right? Because these are both of my restrictions. So if I have two restrictions, which are the squared and cube term, the unrestricted model was actually, or sorry, the unrestricted. The restricted model was just actually just the linear term. So here I can't say the cubic relationship is any better than estimating that linear relationship. But we had some evidence that estimating this as a quadratic relationship was maybe a better fit, right? Just outside of our kind of conventional levels. But maybe if I had a higher sample size, maybe I actually do see that I could say that that square term should be included. And that the nonlinear relationship where I only have a quadratic term is a little bit better than just the linear term. Yeah. Any questions on that before we keep hop back to the slides here? So take a little bit of a step back, but since we were in Stata, I wanted to do all that. So let's say we go back to just thinking about that square term. Oh, what do I want here? We already talked about this. So I think this was a slightly different sample that I took just to kind of have some different numbers. But you can kind of see here, if these were my results, right? It looks like I can say this is statistically significant at what levels? So if my p-value is 0.025, that squared term is statistically significant at 10 and 5%. Now I also can see my r squared went from, oh, maybe I had them in the slide. There we go. My r squared, if I just use the linear model, was 0.05 and it went up to 0.07. Right? So we know that by including it, my r squared has to go up. But can I say that it went up at a statistically significant level? Well, I could run that joint significance test. Once again, it's just for one variable, so it's gonna be pretty similar to what I see on the individual coefficient. What's another thing I could compare here? And we haven't really necessarily done this a lot, but we have all the tools. So what accounts for the fact that I'm using more variables in my second regression? Not my R squared, but my adjusted R squared, right? So in fact, I have the same sample sizes here. So this is a question that maybe showed up on the exam. And it's kind of hard. I closed down some of the things on the exam so you can answer this. Here it's a little bit trickier, but we can see it still holds. So I know that my R squared will go up, right? But what's impacted by the fact that I added an additional variable? My R squared, it's impacted in the sense that I might be able to explain more. But what's happening to my adjusted R squared as I add more variables in? It's going down even more. Like the more restrictions I add in, or the more, not the restrictions, I should say, the more additional variables I add in there, I think it was K was represented in the equation. My adjusted R squared is going to be impacted even more than that. So notice the difference between my R squared and my adjusted R squared from the simple linear model is about what, 0.004. What should happen to the gap between my R squared and my adjusted R squared when I now have not just one, but two? That gap should grow. Sure enough, I've got what? 0.008. So it almost doubled in size there, right? The gap in between my R squared and my adjusted R squared got quite a bit larger, and that's because I'm now using more variables, twice as many, going from 1 to 2, right? And a lot of the examples we looked at, we might have had other control variables in there, and so it did, we were going from like, 5 to 7 or something like that. But here, going from 1 to 2, that could cause a pretty sizable increase in that gap. But given that our adjusted R squared is adjusting for that we've used another variable, if I compare the adjusted R squared from my quadratic model to the adjusted R squared from my linear model, that should be good evidence that if the adjusted R squared is higher, that nonlinear model is better at predicting my Y variable. So I look here, what happened to my adjusted R squared from the linear model was 0.05. Quadratic or nonlinear model, 0.06. So using the adjusted R squared, just another kind of evidence that maybe this squared term should be included in my regression, right? It actually increased not just my R squared, but my adjusted R squared, accounting for the fact that I had to include an additional variable in order to kind of see that increase in R squared. All right, so we already talked about, we know R squared is going to be larger. We can compare instead the adjusted R squared because it accounts for the fact that we use another variable. And then we already talked about the cubic stuff, right? We can run these joint hypothesis tests. The kind of key here was when we run these joint hypothesis tests for both a squared and a cubed term, the comparison that we're making is between the cubed model and just the linear model, not to the quadratic, right? We're doing joint significance testing. So we're saying, does this cubic relationship look better than the linear model? And we have no additional terms, just that linear term. Excuse me. Any other questions on that? All right. What do I want to do here? So we already kind of looked at this already. Kind of ran this in Stata. We kind of saw the F test for this cubed and squared term. The next thing that I want to talk through, and I won't ask you as specific of questions as we did before when we were assigning bias, but just the general idea is important. So can omitted variables impact the statistical significance I see on that squared term, or even the joint significance that we're testing if I had a squared and a cubed term? So the short answer is yes, right? So I'll kind of walk through why. So I think I have the, things that are left out here, but basically I could have omitted variables that are correlated with the nonlinear component of the relationship, but not with the linear component. So we'll kind of walk through the mathematics of what this would look like, and I think it'll make a little bit more sense. So let's say, what example did I use last? I think I did, well, I'll think of one that I like right now. Let's say I'm trying to predict income, and equals. Got my intercept, I've got experience measured in years, I've got my experience squared value, so I'm allowing this to be a nonlinear relationship. Okay. When I estimate both of these, so here's my coefficient on the linear term, here's my coefficient on the quadratic term. Okay. It could be, right, I should see the true effect of both the linear and the nonlinear term. But if I have an important omitted variable, we said we're going to have some additional bias. Okay. So if there's this third variable that I could have included, but instead I omitted it, which is, I don't know, parental income, right? So I could have included this third variable, but I omitted it, right? How would that influence the results that I see if I do omit that variable, right? If I don't include this, right? Well, it's going to be whatever effect that omitted variable would have had on my y variable. So whatever effect parental income would have had on how much income I'm generating, multiplied by the covariance of that omitted variable. So kind of parental income or like your family's income level. Thinking about things like nepotism or something here. However, here, it's going to be the correlation of parental income with just experience. Down here, it's going to be the correlation or the covariance of parental income with experience, squared. Divided by the variance of whatever variable you included, divided by the variance of whatever variable we're thinking about here was included. So if these covariances are different, then the size of the bias will be different in my linear versus my nonlinear term. So I don't know, this one I was kind of thinking about, maybe parental income doesn't look like it's really impacted with your experience. You're not given that many additional opportunities just because your parents were making additional $10,000, $20,000. But maybe if you take that parental income and square it, really large values, like if we went to the extreme ends of parental income, maybe there we see that it has some impact, we're thinking about large levels of experience, maybe parental income there really allowed you to kind of have additional opportunities that a lot of other people didn't early on. And so these experience squared measures might be a lot larger. Maybe we do pick up a larger covariance there. So this is just kind of writing it out, thinking about the bias that exists in the nonlinear and the linear term. Because these aren't the same, right? Could be different. Right? So we could have a slightly different bias there. Any questions before we keep moving here? And I won't in these ones, it's not like I'm gonna go back like we were before and try to put a sign to this bias or anything like that. But just understanding that if we do have omitted variables, it's still an issue, right? And not only is it an issue, it's an issue in that it can prevent us from seeing that the nonlinear relationship is actually better, right? Because it might provide coefficient estimates that are biased towards zero, right? It might actually look like there is no nonlinear relationship. Right?